Well, thank you very much for the invitation. It's a great pleasure to come to Torino. It's a great pleasure to be able to travel again. It's a great pleasure to see all of you in person. So thank you very much for the invitation. I want to talk about some work I've been doing with Rajesh Gopakumar, particularly this last year, but it builds on work we've been doing over the last almost 10 years or so. So let me start by reminding you about sort of basically how ADS-CFT works, because our aim is to understand ADS-CFT sort of in a fundamental way, in some sense, to prove ADS-CFT. So what's important for us is how the different sides of the correspondence are related to one another. So on the left-hand side, I've drawn the quantities that pertain to string theory on ADS cross S, say ADS5 cross S5. And on the right-hand side, I've written the quantities as they appear from the gauge theory side. So the rank of the gauge group, this is something you probably all know, is related to the radius in Planck units, and the Tuft parameter, which is the effective coupling constant of the gauge theory at large n, i.e. g squared Young-Mills times n, is related to the radius in string units to some appropriate power. So this is obviously only approximately true, but this is sort of true in the supergravity regime. And we can ask what's the corner of a weakly coupled gauge theory, weakly coupled planar gauge theory. So planar would mean you take n goes to infinity, which would mean you take the radius large in Planck units. And if it's weakly coupled, then the Tuft parameter must be small. And if you follow this dictionary, what it tells you is that the radius of the ADS space in string units must be small, which is another way of saying that the string scale must be large, so that the radius is essentially of the same order of magnitude as the string scale. So this is something that's commonly referred to as the tensionless limit of string theory. That's the limit where the typical size of the string is very, very large. And this is what this LS parameter describes. So this is an old observation that the dual of free super Young-Mills will correspond to tensionless string theory. So this is string theory in the regime where the string is very long. So it's the opposite regime from the supergravity regime. So people often say ADS-CFT is a strong weak coupling duality, because from the point of view of supergravity, this tensionless regime is very, very far, very, very non-perturbative. But from the point of view of string theory, it's just this regime where the string tension is very, very small. Now, this is the regime where ADS-CFT becomes perturbative, or where you could hope to have a chance to prove ADS-CFT correspondence. So on the gauge theory side, this is obvious because that is weakly coupled. So that's obviously under perturbative control. And as I said, on the string theory side, we are very stringy, very far from supergravity, but it's in some sense the maximally symmetric point of string theory. It's the point where these stringy excitations become massless, and therefore string theory develops a much bigger symmetry algebra than it would otherwise have. That just reflects the fact that free super Young-Mills has a much bigger symmetry, and therefore, again, fits together with this dictionary. Now you can ask, how could you hope to prove the ADS-CFT correspondence? So here you have something under control. Here you've just said some nice words. You've said tensionless strings, but you don't really have a handle on it because it's far from the supergravity regime. So how could you hope to make it concrete? And our working hypothesis, our idea is that while this may be very complicated, or while it is very complicated from a supergravity perspective, our working hypothesis is that it's going to be very simple from a worldsheet perspective, from the perspective of fundamental string theory, i.e., and that's what I want to convince you of, is that what's special about a string dual of free or weakly coupled super Young-Mills is that it has a free field worldsheet description. And a free field worldsheet description is, again, something you'll be able to study, analyze, calculate, whatever you want. And therefore, this is something where you have things here under control if you work with the worldsheet, and you can hope to directly prove that this matches with the perturbative weakly coupled super Young-Mills description. There was a question here.
Thanks. Excuse me, if I remember well, the reference you gave in the end, this is connected somehow to the fact that you have some higher string theory, like Vasiliev theory, in this regime, something like this? Sundell and the others
yes, exactly.
went in that direction, although this is a conjecture as far as I remember, something like this.
So this will not directly play a role for us, although our theory does exhibit a higher spin symmetry.
String theory is supposed to land on this higher spin theory?
Well, so the higher spin theory will be a subsector of string theory.
Yes.
It will just describe the leading Wedge trajectory, but our worldsheet theory will have such a subsector. So it will have embedded inside it the Vasiljev theory, although the way we'll describe it is as a full-blown worldsheet string theory.
Without any mention of higher spin theory.
Yeah, so this is the last slide where higher spin will appear. So higher spin will secretly maybe be doing its magic in the background, but it will not be manifestly playing any role.
Oh, okay.
But you'll see.
But okay.
You'll see. Okay, so this is our working hypothesis. Our working hypothesis is there's a chance to prove ADS-CFT because weakly coupled gauge theory could be distinguished by the fact that the worldsheet description is free, not supergravity. Supergravity will be highly complicated, but the worldsheet description could be free. Now, these are just words. So what is the evidence in favor of these words? Well, the first evidence comes, and that I believe we have very good and very concrete evidence for, is for the case of ADS3. So string theory and ADS3 cross S3 cross T4 is believed to be dual to, people usually say, the symmetric orbifold of T4. What they really mean by this is if you pick some random string theory describing this background, it'll be dual to a conformal field theory that lives on the same moduli space as the symmetric orbifold of T4. The symmetric orbifold of T4 is a specific conformal field theory, but it has exactly marginal operators, so you can move around in a moduli space that is generated by the exactly marginal operators. And the claim is that string theory is dual to one such CFT on this moduli space. Now you can ask, what's the analog of free supermills in this context? Now, the almost obvious suggestion is that the analog of free supermills should be the symmetric orbifold theory itself. Because you see, the symmetric orbifold theory is the theory of 4n free fermions and 4n free bosons modulo to some global symmetry. So you would think that this is like the analog of free supermills. So you can ask, so if our basic picture is right, that the weakly coupled theory should have a free worldsheet description, what this should mean is that there should be something simple about the dual of the symmetric orbifold theory, the worldsheet theory that describes the symmetric orbifold theory. Now we've shown, and this goes back to work I've done together with Rajesh and Lawrence Eberhardt a number of years already, that the correct worldsheet description is this hybrid formalism of Berkowitz-Waffer-Witten, which is a Wessel-Mino-Witten model based on PSU 1,1/2 at level 1, together with the T4 degrees of freedom, which I'm suppressing here. And what's crucial in order for this to work is that this theory has a free field realization in terms of free fields on the worldsheet. So this has a free worldsheet theory in terms of symplectic bosons and free fermions. Don't worry if you don't know what symplectic bosons are, I'll explain this later on. What's important here is that they are free fields. So this is a free worldsheet theory. And what we've shown is that if you include the spectrally flowed representations, as was already proposed by Maldacena-Oguri in the original description of ADS3, then the space-time spectrum of this worldsheet theory matches exactly the single particle spectrum of the dual symmetric orbifold. So this is an example where this idea is realized, where we have the analog of free supermills, the symmetric orbifold theory, being described by a free worldsheet theory. Now, our proposal is that this is the right way to try to generalize to ADS5 cross S5. So more specifically, what we propose is that for the case of free n equals to 4 supermills, what characterizes the worldsheet theory is that it's the appropriate generalization of this free field theory for the case of ADS3 cross S3. Namely, it's instead of having 4 symplectic bosons and 4 free fermions, you just double the degrees of freedom. So you take 8 symplectic bosons and 8 free fermions, they're again free fields. The reason why this is plausible, and I'll explain this to you in more detail as we proceed, is that they lead to a free field realization of the super Lie algebra or the super affine Lie algebra PSU 2,2/4, again at level 1, and PSU 2,2/4 is the global symmetry of n equals to 4 supermills. So at least the global symmetry of this worldsheet description will come out right, because the zero modes of these currents on the worldsheet will map physical states to physical states, and therefore the physical states will automatically sit in representations of PSU 2,2/4. So that's already a good starting point in order to match with n equals to 4 supermills. Now, similar theories have actually been considered before, in particular by Berkowitz, but the new ingredient, or one of the new ingredients, is that the generalization from ADS3 suggests that what we should do, just like there, is include these spectrally flowed representations. So I'll explain to you what these spectrally flowed representations are, and then I'll explain to you that if we take this idea seriously, then we end up with a worldsheet theory whose space-time spectrum matches exactly that of free n equals to 4 super mills in the planar limit of free n equals to 4 super mills. So this is our proposal. Now, I say here a natural quantization, so there are certain issues here we haven't completely sorted out. There's a bit of a leap of faith involved here, and I'll be open and honest with you about it. But this is a candidate of a worldsheet description that would fulfill this hope that I outlined in the first slide, namely being the worldsheet description that matches exactly free n equals to 4 super mills, and thereby open the door towards the proof of the ADS-CFT correspondence for the case of ADS5 cross S5, because the worldsheet theory, being a free field theory, will be something we'll have under control and will be able to check all of these statements, whether they match with free n equals to 4 super mills. So this is the outline of what I want to explain to you. And in the rest of the talk, I want to give you a bit more details. So this is sort of the scientific American version. And now we are I'll try to explain to you more specifically how this works. And what I want to do is I want to first explain to you as briefly as I can, but keeping track of the salient features of how it works for ADS3 cross S3. And then I'll explain to you how our proposal is for how to generalize this to ADS5. Okay, so I try not to bore you with ADS3 cross S3. I really try to sort of highlight the key elements that will work similarly. So as I mentioned before, what's key is this PSU 1,1/2 Wessel-Witten model that appears in this hybrid description of Berkowitz, Waffer, and Witten. And so you have this, and then you have a topologically twisted sigma model for T4. So this is just a fancy way of saying that you have 4 bosons, and the 4 fermions that used to be spin 1/2, 2 become spin 0 and 2 become spin 1/2, spin 1 after some topological twist. And this is the proposal of Berkowitz, Waffer, Witten, how you describe string theory in ADS3 cross S3 cross T4. And it's been checked that this agrees with the Maldacena-Oguri description that's maybe more familiar to many people for generic level. Now, what's special about this level 1 theory is that it has a free field realization. And in our way of looking at it, that's just signifying that it's dual to a free field theory. So what is this free field realization? Well, we have 4 symplectic bosons. So what these are beta gamma systems of spin 1/2 fields. So Xi, and so this is your small exercise in Greek letters. So Xi and eta are symplectic boson fields. They both have spin 1/2. And what symplectic boson means is they satisfy a commutation relation that looks as though it wants to be the anti-commutation relation of a fermion. So they behave like spin 1/2 fields, but they satisfy commutation relations rather than anti-commutation relations. So it's like a beta gamma system that you are probably familiar with from the quantization of string. And the fermions are just standard fermions. They are just 4 real fermions that satisfy this sort of anti-commutation relation. And then what you can check is that the bilinears in this field generate the super affine Kac-Moody algebra U 1,1/2 at level 1. And then in order to reduce this to PSU, which is what you want for ADS3 cross S3, one has to gauge by a diagonal U1, and this is the form of the diagonal U1. You basically pair them together, the 2 symplectic bosons and the 2 fermions, and you have to quotient by the Z and Z it to 0 in order to go to PSU 1,1/2. Now, what's key for the following is to understand this spectrally flowed representation. So let me spend a few minutes explaining to you how they come about. Now, a free field theory, you probably all know what sort of representations it has. So it is symplectic bosons and the fermions. Let's take them to be in the NS sector. Then they're all half integer moded. And then there's a ground state that's killed by all the positive modes, and all the negative modes produce your Fock space. Okay, so that's the one highest grade representation you know. And the other one is where all of them live in the Ramond sector, where all of them are integer moded. You see, because the bilinears want to be the things in U 1,1/2, and they should be integer moded, either all of them are half integer moded or all of them are integer moded. So that we have either a Ramond sector or an Schwartz sector. And here is a caricature of what the Ramond sector looks like. So you have some ground states on which all the positive modes kill, and then the negative modes fill up some Fock space. And on the ground states, you have zero modes, and the zero modes basically move you up and down along here. And the representation on the highest weight space is what you may want to call the singleton representation of PSU 1,1/2. It's sort of the smallest non-trivial representation of PSU 1,1/2. Now, the idea of spectral flow is that these representations are not sufficient to describe string theory. And the reason for that is in some sense obvious. If you think about string theory in flat space, you see, you have to satisfy the Maschel condition. Say in bosonic string theory, L0 is equal to 1, but you want to have arbitrarily many excitations. So in order for that to be possible, the L0 spectrum of the representation must be unbounded, because otherwise you can't have many excitations and still satisfy L0 is equal to 1. So how do you get naturally unbounded representations out of these fields? Well, what you do is you do what's called spectral flow. So what this means is there is an automorphism of the symplectic bosons and also the fermions, but on this slide, I'll just concentrate on the symplectic bosons, where you move them up and down by W/2. And given the simple form of the free field commutation relations, obviously, these guys satisfy the same commutation relations as the ones before, because those that get mapped together in pairs, one gets moved up and one gets moved down, and therefore the commutation relation will be happily the same. So the idea is you start with your standard Ramond sector representation, say the one you are familiar with, and you interpret it as the representation with respect to the tilde modes. So the tilde modes act on the standard highest rate representation, and then you simply decide that you look at this space with respect to the action of the untilde modes that are shifted up and down. So it's the same underlying vector space, but you're modifying the way in which the symplectic boson generators act on it. And therefore, you're modifying the way in which the bilinears of the symplectic boson generators act on it. And in particular, the Cartan generator of SL2 gets shifted by W/2, and the L0 generator gets shifted in this manner. L0 is L0 tilde minus WJ30 tilde minus a constant. Now, the details are not maybe that important, but what's important is that you see now this L0 spectrum, the L0 spectrum will now not be bounded from below, because you see why L0 tilde is bounded from below, J30 tilde is not bounded from below. In particular, if you go to positive J30, so all the stuff that's over here, you can make L0 as negative as you want, so you get an unbounded L0 spectrum. But because it's inherited from a consistent representation simply by an automorphism, it's another consistent representation. So these are the representations which Maldaceno and Oguri proposed you have to add to your usual representation in order to describe string theory in ADS3 cos S3. And we shall do exactly the same thing here in this hybrid formalism of Berkowitz, Waffer, and Whittle. Okay, so this is spectral flow, how it roughly works, and it gives you rise to a natural family of representation. And according to Maldaceno and Oguri, these are the representations you have to include in order to describe string theory in ADS3. So these generators, these untilde generators, then act on the spectrally flowed vacuum. Now, the spectral flow doesn't just shift the J3, the Cartan generator of the SL2. If I spectrally flow also the fermions, it also shifts the SU2 generator. And it also, then the L0 shift takes this form if you also spectrally flow the fermions. And what you see from that is that the ground state will be a BPS state with respect to the space-time theory for any value of W, because it will remain physical. So on the ground state, J30 and K30 are 0. And then under spectral flow, you just shift up the eigenvalues by W/2, but the SL2 and the SU2 eigenvalues get shifted up by the same amount, and therefore the BPS condition will remain intact. So this is part of the spectrum, but then obviously you have all the descendants from it. This is just the ground state of this spectrally flowed sector. Now, again, I could give a whole lecture to explain to you how you exactly get the symmetric orbifold spectrum out of this, but there's basically an easy way to think about how this works. So think about it. U1,1/2 has 4 symplectic bosons. But I told you, you have to divide out by this U1 generator, because you have basically, I mean, you want to describe P as U rather than U. So when you divide out by the U1 generator, you basically lose 2 of the bosons, like you usually use in string theory. You look at the states that are annihilated by the positive modes, and then the negative modes become spurious states. So you kill 2 sets of oscillators. So of the 4 bosons that you started off from, 2 gets killed by the coset condition that reduce you from u1,1/2 to p as u1,1/2. But now we still have to impose the usual physical state condition of string theory. And as we all know, that eats another 2 bosonic degrees of freedom. So following that logic, what you conclude is that of the 4 degrees of freedom that ADS3 cross S3 contributed to the whole worldsheet theory, all 4 of them get removed by the physical state condition. So the only thing that's left behind are the bosonic degrees of freedom that come from the T4. So the space-time spectrum will basically look like a T4-like space-time spectrum, except we have this spectral flow parameter. And what will turn out, if you look at this carefully, is that the W spectrally flowed sector simply becomes the W cycle twisted sector of the symmetric orbifold of T4. And you reproduce exactly the single particle spectrum of the symmetric orbifold of T4 in the larger limit. There's a question by Alessandro.
I got a little bit confused because I agree that when you go from U something to PSU, you want to get rid of essentially 2 U1s, and that works with your counting. I got a bit confused. How is that one condition that you impose actually count for 2 U1s? It's not obvious to me.
Well, so you have to impose. So the condition you have to impose is that the positive modes kill physical states. But the Z operator is actually a null operator in the sense that its commutator with itself is 0. And therefore, what this means, once you impose that the Zn conditions kill, the Z minus n modes are spurious, i.e. they are null and decoupled from the physical spectrum. So you lose, it works exactly like the Virasoro condition. In the Virasoro condition, the Ln's kill, but then the L minus n's become spurious. So the U1 condition kills you 2 bosonic degrees of freedom, and you end up with just 2 bosonic degrees of freedom. Then the usual Virasoro type mass shell condition gets rid of them, and you just add now with the physical spectrum of the symmetric orbifold. So that's as regards the spectrum. Now, I also briefly want to mention how this works on the correlation functions. Now, this is a somewhat more technical topic, so I just want to sort of give you a vague flavor of how this works. So, in fact, something quite remarkable happens. If you calculate the correlators on the worldsheet, what you find is that they are mostly 0. In fact, they are delta function localized to those coordinates. So the Zi are the worldsheet coordinates. The Xi are the space-time coordinate where you insert the corresponding operator on the dual CFT. And what you find is that these correlation functions, and that follows from an analysis of the Ward identities, are delta function localized to those Zi's that admit a holomorphic covering map from the Z's to the X's, i.e. a map of the form that maps Z to Xi plus some number times Z minus Zi to the Wi if Z is near to Zi. And that's a very restrictive condition. There are holomorphic covering maps. There are few of them around. There are only discretely many. So as a consequence, this becomes a sum. And then you can easily do the modular integral that you are instructed to do in string theory. And out of this modular integral, you just pick up a sum over all the holomorphic covering maps. And in fact, that's one way in which you can calculate symmetric orbifold correlators according to the word of Lunin and Matur. So in some sense, manifestly, you recover the structure of the symmetric orbifold correlators from the worldsheet perspective, but it hinges on the fact that these worldsheet correlators have this very remarkable localization property. And this is something which we proved in this more recent paper together with also Andrea, who is in the audience, where we showed this, that this is a consequence of the Ward identities of this free field theory. So this is not just some wishful thinking. This is something that follows from a careful analysis of the properties of this worldsheet CFT. And in fact, in this context, it looks very much like the incidence relation in twistor theory, and that was part of our inspirations for how to try to generalize this to ADS5. So in this paper, we proved that the correlators actually satisfy this identity, where gamma is the covering map, and that looks as though that psi minus and psi plus are the spinor variables of some twistor description of the 2D space-time. Okay, so this is my lightning review of ADS3, and now what we want to do is we want to, and I'll be more speculative in the following, we want to generalize it to ADS5, so I'll explain to you how we believe we can generalize this, and then I'll explain to you what evidence we have that this is the correct thing to do. So our bold proposal is that what you should do in order to describe the worldsheet theory describing free superhang Mills is simply you replace the 4 symplectic bosons by 8 and the 4 real fermions by 8 real fermions. And as I'll explain to you on the following slide, they'll generate U2,2/4 at level 1 And then if you divide out by an overall U1, you'll get P as U2,2/4 at level 1. And as I mentioned before, that will guarantee that a space-time spectrum will have the correct global symmetry. Now, how does this work more explicitly? So the worldsheet fields are the following fields. So they're the yi's and the zi's. So alpha and alpha dot are spinor variables with respect to an SU2. So you have two of these, two of these, two of these, and two of these. So these are your 8 symplectic bosons. And A is a vector index with respect to SU4. So you have 4 of these and 4 of these. And they satisfy the standard free field commutation relations. The fermions are just the standard fermions, and the symplectic bosons are just 2 pairs of what we had before. And obviously, the alpha guys talk to the alpha guys, and the dotted guys talk to the dotted guys. In fact, this is very similar to this old twistor string proposal of Berkowitz, and it's inspired by the fact that the twistor space of ADS5 is the ambi-twistor space of C4, and this looks a little bit like an ambi-twistor description of that. But the details of this are not entirely clear to us. This is more of a generic inspiration that maybe something like that could be right. Now, what we should do is we are going to look at the bilinears where we take one generator from the y's and one generator from the z's, and then you can convince yourself that these generators produce the super affine Kac-Moody algebra U2,2/4 at level 1. And in order to obtain P as U, you have to divide by the analog of what I called Z before, and I'll call C here. And the nomenclature we are following here is very much based on the usual oscillator construction of P as U2,2/4 that people in the Spinchain community, in your community, will be very familiar with. In fact, this is really the affinization of the oscillator construction of P as U2,2/4. I mean, the oscillator construction would be if all of these modes just were 0 modes. Then I would just get the standard oscillator construction. Now I simply promote them to be modes of some conformal field, and then I'm going to get the affine version of it, and I'm getting the affine version at level 1, as it turns out. But this is, in some sense, a familiar construction to you. So this is another reassuring effect that this somehow seems to tie naturally with what the Spinchain description of the string theory in ADS5 versus 5 may look like. Okay, so this is the free fields that we have, and now we have to declare what are the representations that appear on the worldsheet. So this is the place where we'll be inspired by ADS3, following the spectral flow operation as it was occurring for ADS3. So what did you do for ADS3? So for ADS3, you see you shifted these mode numbers up and down by W/2, and whether you shifted them up or down depended on their eigenvalue under J30 minus K30, and J30 became the conformal dimension of the dual CFT. That's the SL2 Möbius group of the dual CFT, and K30 is the Cartan generator of the SU2. Now, the generalization to ADS5 is that you should replace the conformal dimension by the dilatation operator of n equals to 4, and this Cartan generator of SU2 with a certain Cartan generator of SU4. So that's our proposal for what spectral flow should be. You should shift these modes up and down depending on their eigenvalue under D0 minus R0, where D0 and R0 are the familiar generators that appear in P as U2,2/4. And then we do exactly the same as before, except here it's slightly more convenient to start from the Ramond sector, but that's a rather minor technical issue. Sorry, from the Neveu-Schwarz sector, that's a rather minor technical issue. So we start with the Neveu-Schwarz sector ground state. We start with them being half integer moded. So with respect to the tilde modes, all the positive modes annihilate and all the negative modes create. And then if you just look at this dictionary, so for example, this dictionary tells you that the ground state will be killed if R is a half or bigger. So this means that with respect to the untilde modes, it will be killed if the mode is greater or equal than W+1/2, right? Because the half here becomes a half plus W/2. So for all the modes that get shifted upwards, namely these, and these, the ground state is annihilated by the modes that are more positive than W+1/2. And for the other ones that are shifted downwards, it obviously works the other way around. Again, that's just sort of translating exactly what happened for ADS3 to the ADS5 setting. Now, also, as for ADS3, the various currents of PSU1,1, PSU2,2/4, they will pick up correction terms, normal ordering terms under spectral flow. And if you work this out, what you find is that the dilatation operator gets shifted upwards by W. This Cartan generator of SU4 gets shifted up by W, whereas the central generator, the C generator, will stay invariant, so that states that satisfy Z equal to 0 get mapped to states that satisfy Z equal to 0. And furthermore, the stress energy tensor, the worldsheet stress energy tensor, picks up this term that looks a little bit like this BMN-like correction term. And importantly, what you find is that the ground state is the physical BMN vacuum, because the ground state, all the tilde modes before spectral flow are 0. So this term will be 0. So they will continue to satisfy L0 is equal to 0, but their eigenvalue under D0 and R0 get shifted up by W. So they look exactly like the BMN, physical BMN BPS state. Okay, so this is our proposal for what this worldsheet theory is. You take these free fields, you take this Navier-Schwartz sector representation plus all its spectrally flowed images, where you apply spectrally flow the same amount left and right. Now, now you have to impose the physical state condition. So first of all, we have to understand what does the Fock space look like that you generate that way. Now remember, these are free fields. So if you know which modes kill the ground state, then the complement of these modes will act freely because it's a free field theory. So if the mu's kill if R is greater than W plus 1 over 2, then they will create if R is less than W minus 1 over 2. So for the modes in the first line, this is the condition. And then for any of the modes, it's if R is less than equal to minus W plus 1 over 2. So obviously I could have written the second line just with this, and in the first line remove the lower bound. But the way I want to organize it is that I say all the modes of the first line act non-trivially if they lie in this wedge, and then everybody acts non-trivially if the mode number is sufficiently negative. So this is just a statement about this spectrally flowed Fock space. So there's nothing to debate here. Now the question is, what should the physical state condition amount to? Now in the case of Berkowitz-Waffer-Witten, there was a prescription of what we have to do. We have to calculate a certain cohomology, and you should only retain the states that survive in that cohomology. Here we are on our own. Berkowitz-Waffer-Witten haven't yet told us what the correct physical state description is. So here we make a proposal, and the proposal is a bit of a bold proposal, but we think it's a rather natural proposal. You see, this theory has twice as many supersymmetry as the ADS3 theory, because instead of having 4 plus 4, you now have 8 plus 8. Now the Berkowitz-Waffer-Witten theory has an n equals to 2 worldsheet theory symmetry, and it's very plausible to believe that this will have an n equals to 4 worldsheet supersymmetry. And therefore, you could entertain the idea that the correct physical state condition is the one where you look at the critical n equals to 4 string, i.e. you demand that all the n equals to the positive modes of all the n equals to 4 generator kill physical states, and then the negative modes will produce spurious states. Now, if you entertain this idea, then you see n equals to 4 generators have 4 bosons and 4 fermionic generators. The n equals to 4 means 4 supercurrents, and then there's the stress energy tensor plus the 3 SU2 currents, so there are 4 bosonic and 4 fermionic currents. So if you look at the critical n equals to 4 string, it will kill 4 bosons and 4 fermions from asking the physical states to be killed by it, and 4 plus 4 from removing the spurious states. So it will remove 8 bosonic descendants and 8 fermionic descendants. So basically, it'll remove everything. Now, that's the hallmark of a topological theory. And our proposal is that's the correct description in order to get the worldsheet description that matches 3 super Mills. But what we mean by all of them is that we mean all of the modes that are sufficiently negative. So our proposal is that this critical n equals to 4 constraint will remove all of the modes whose mode numbers are sufficiently negative, and it will retain the modes that live inside this wedge. And the idea is that these wedge modes you should think of as being 0 modes rather than non-zero modes. You should think of them as being shared between left and right moving degrees of freedom, because if you analyze this Berkowitz string theory, there are certain U1 flux solutions, and these U1 flux solutions have a certain number of holomorphic modes, and these holomorphic modes of this flux solution look exactly like the modes that we retain here. So our proposal is that this yet to be precisely defined physical state condition will amount to removing all of these modes and retaining the wedge modes subject to some residual gauge conditions that I'm describing on the next slide. And I'll be totally clear with you. This is a postulate at this stage. We haven't yet constructed a cohomology, but what we propose is that there is a cohomology that will achieve that, and that is the correct description of string theory to describe string theory in ADS5 process 5 in a tensionless limit to match free superhang mills. Okay, so let's just take, for the sake of argument, believe me that that is a reasonable thing to do, and let's analyze what the consequences of these are. Now, as I said, we still have to impose two residual gauge conditions. You see, one residual gauge condition comes from the fact that the central term we haven't yet taken care of. If you just were to take all of these modes, you would produce states where the central charge would not be zero, i.e. they would fall out of PSU 2,2/4. So we want to impose that all the positive Cn modes are zero. And then we want to impose something that looks a little bit like a mass shell condition, a Virasoro condition. And again, this is a bit of a proposal, but what we propose is that the correct condition is this residual U1 condition plus the condition that the L0 eigenvalue on the worldsheet must be a multiple of W in order for the state to be physical. Now, the intuition here is that, remember, this ground state looks like the BMN vacuum with P plus equal to W. So W seems to play the role of P plus. And then if you blindly open BMN and you take the formula for P minus and you go to the tensionless limit would mean this term disappears. This will just become a constant. Then this sort of a light cone Virasoro condition would become this condition. So this is, again, a postulate. Once one has found a first principle derivation of this physical state condition, this should be derived. But at this moment, we just postulate that that's the outcome of that physical state condition. Now, if you buy all of that, then we can show that you reproduce exactly the spectrum of free superhang mills in the planar limit. Now, in fact, that's not too hard to see how this comes about. So let me talk you through the argument. So you see, we have these wedge modes, and these wedge modes are really have mode numbers between minus W minus 1 over 2 and W minus 1 over 2. So we want to think of them as being the momentum modes associated to some discrete Fourier transformation of position operators. So we do an inverse Fourier transformation to define position operators. We end up with W position operators. And if you take the commutation relations of these momentum modes and translate them via this Fourier transformation, what you deduce is that the position operators at different positions pairwise commute. So you can think of them as being a certain number of wedge modes, or you can think of them as being W position operators. And that's beginning to look a little bit like a spin chain. That looks like a spin chain with W many sides, where at each side, the excitations are described by these Zs and the Ys, which are these twistor variables from which I started. Now remember, I have to impose this residual gauge condition that Cn is equal to 0. Again, if you sort of Fourier transform this, what you see is what this amounts to is that at each side separately, C has to be equal to 0. That is exactly what this condition becomes once you've written it in terms of this side form in this fashion. So what this means is that at each point, you have these twistor variables, but they satisfy Z equal to 0 at each of these points, which means that at each of these points, you have an oscillator construction of the singleton representation of PSU 2,2/4 city. So it looks like a spin chain with W sides. At each side, you have the singleton representation. And this condition simply becomes the cyclic invariance under this W-fold tensor product. So what you end up with is the W-fold tensor product of the singleton representation modulo cyclicity, but that is exactly the spectrum of free superhang mills in the planar limit. So in this way, you see that what's left behind after this gauge fixing procedure matches exactly the physical spectrum of free superhang mills. And the picture you should take away from here is that you see the spectrum of free superhang mills are all the traces of all the fields you can make. The fields you can make are derivatives of the bosons and the fermions and the field strengths. These are exactly in one-to-one correspondence with the elements of the singleton representation. So you take W of them, you take the traceless combination, and what they come from is this W spectrally flowed sector of this free symplectic boson and fermion theory. So this looks as though that the string theory is really becoming to be a string bit description, where each string bit is this twistor valued string bit, and you're gluing W many togethers to describe the sector with W fields in superhang mills. And when you sum over all W, you reproduce the full n equals to 4 spectrum. Okay, so this is our proposal. Now, there are some neat features that appear that we would love to understand better and see what they really mean. So for example, you can ask, how can I make the physical state? So you see, I'm taking these wedge modes, but I still have to satisfy these conditions. So this condition you can satisfy by forming what you may want to call DDF-like operators. These are operators that basically commute with the C condition and therefore map physical states to physical states. And what we've shown is that all the physical states you can make by taking these DDF-like operators and acting with them on the ground state. Now, these DDF-like operators, they satisfy some interesting algebraic structure. They satisfy some sort of commutation relations that looks, this isn't quite a Youngian, but it sort of feels like the same ballpark of animals. So this is somehow lurking inside this description. That's sort of the spectrum generating algebra from the worldsheet perspective. Now, in particular, this will guarantee that everything falls into representation of PSU 2,2/4 because the zero modes of these DDF operators are precisely a copy of PSU 2,2/4 and will therefore guarantee that the spectrum falls in these representations. So for example, if you act on the W spectrally flowed ground state, you simply produce the full BPS multiplet, the full PSU 2,2/4 multiplet that contains the BPS state, but then obviously the other ones will come higher up. So for example, when you look at small w, for w equal to 0, you just retain the vacuum state. For w equal to 1, you just have zero mode, so you actually get just the BPS singleton representation. That's a representation that's absent in SUN. It would be present in UN, so we just remove it by hand. And then for w equals to 2, you begin to see more of the interesting structure. So at L equal to 0, you get a BPS representation. At L equals to -2, you get a Konishi multiplet that's generated by the 4 positively moded fermions acting on the twisted sector ground state. And then all the other multiplets that appear, the higher spin multiplets, they come from higher powers of these DDF operators acting on the twisted sector ground state. Now for w equals to 2, that still looks vaguely simple. For w equals to 3, the structure is more complicated. So here is a table that I've taken from this paper of Bianchi, Morales, and Samtleben. You're not meant to read it. You're meant to see that it contains lots of stuff, which I hope you can do. And you're meant to take away that apart from having this abstract argument, we've actually gone to the trouble to make sure that all of these states are really correctly reproduced by our description, and they are. So this works as expected, but it gives you a slightly new way of looking at this spectrum because this spectrum comes sort of stratified by L0 eigenvalues on the worldsheet, and it may be interesting to look at this spectrum from that perspective. Now, another consistency check we have done is we've applied this wedge construction to the case of ADS3. You see, in the case of ADS3, we have a first principles description of what the physical degrees of freedom are, because that's the cohomology a la Berkowitz, Hofer, and Witten. But we could also take our bold proposal and see what would happen if we applied it to the case of ADS3, i.e. this wedge construction. Now, obviously, you shouldn't expect to see the full spectrum of the symmetric orbifold of T4, because we're only looking at the ADS3 because there's 3 bit. We are sort of blind towards the T4. The T4 don't even appear in our model. So we should only see those degrees of freedom that are independent of the T4, which are sometimes called the compactification independent states of the symmetric orbifold. You see, there's ADS3 cross S3 cross T4, but there's also ADS3 cross S3 cross K3. And so whether it's T4 or K3 shouldn't matter. So we should see those states that appear in both theories. And if you run through this wedge construction, you do indeed see a certain part of the spectrum. In particular, you see the upper BPS state from the W-1 cycle twisted sector, and that is the one that's associated with the 0th cohomology of the additional 4D manifold, i.e. it's independent of whatever this manifold is. It's just associated to a point on this manifold. So this works quite nicely. It also suggests that part of the reason why it has proven so hard to relate the Spinchain description to the symmetric orbifold description is visible from that perspective. You see, our wedge description has more or less manifestly a Spinchain picture embedded in it, because it looks like W copies modulo some cyclic symmetry. Now, if you take this and you translate it into the symmetric orbifold language, what you see is that because of this funny shift of what W is in ADS3, where we measure things relative to the Ramond sector, and ADS5, where we measure them relative to the Ramond sector, the Neveu-Schwartz sector, what you find is that the cyclic symmetry of the spin chain from the point of view of the symmetric orbifold must be a ZW symmetry, but not in the W cycle twisted sector, but in the W minus 1 cycle twisted sector. Now, this is maybe a little bit technical, but for those people who know that there is no obvious ZW symmetry in the W minus 1 cycle twisted sector of the symmetric orbifold. There's an obvious ZW minus 1 symmetry in the W minus 1 cycle twisted sector, but not a ZW symmetry. And the spin chain cyclic symmetry wants to be a ZW symmetry in the W minus 1 cycle twisted sector. And that tells you that from the point of view of the symmetric orbifold, this cyclic symmetry is probably very unobvious. It's probably very hidden. And that's probably the reason why it has proven so hard to see the spin chain description directly from the symmetric orbifold. Also, this really only refers to the ADS3 cross S3 bit. It doesn't see the T4. So again, that's probably also part of the reason why it's proven so difficult to make this correspondence precise. Now, I've been given 1 minute, so let me just conclude. So I've the free field realization of the ADS3 cross S3 worldsheet theory that's dual to the symmetric orbifold suggests a natural generalization to ADS5 cross S5 with some assumptions that we obviously would like to make more firm about the structure of the physical state condition. We've shown that this leads exactly to the right spectrum of n equals to 4 superreals in 4 dimensions. And therefore, this potentially opens the door for a concrete worldsheet model that will directly reproduce free superreals. Now, there's obviously a long list of open questions. So to start with, we should understand this physical state condition from first principles. We are trying to construct this cohomology that will do the trick. Then what we would like to do is, obviously, this is free superreals. We would like to go to interacting superreals. So in order to analyze the perturbation away from the free case, we have to understand the structure of the correlation functions that will appear once you start doing perturbation theory. And the correlation functions of ADS5, you would believe, will follow a similar localization property as for the case of ADS3. So we are quite confident that these correlation functions will be able to get under control, and that will allow us to analyze the perturbation theory away from the free case. Now then, as I was asked about a higher spin symmetry, so higher spin has not played any role in what we do, but somehow it must be lurking in the background. So somehow there should be a manifest higher spin symmetry organizing what we do. The Youngian symmetry should somehow rear its head. This must all appear somehow in this worldsheet description. It would be interesting to understand how this looks like microscopically. Then, as I alluded to, there's a novel way of thinking about the n equals to 4 spectrum in terms of stratifying it by these L0 eigenvalues. That may be a natural way to think about this spectrum even away from this 3 point. And then if you calculate these correlation functions, there are certain aspects of it that look a little bit like what one does in the hexagon approach to calculating correlators for n equals to 4. The fact that you split this up, the hexagon, into 2 pieces and glue them together, that's really this twistor variable description. So it would be interesting to see whether there's more than an analogy here. And then obviously much more. This is all very recent. So there are many, many open problems that it would be good to understand. And I think this is an interesting opportunity to really try to, in some sense, not just prove ADS CFT, but make it manifest by having a description on that will just manifestly reproduce free superreals. And what this description looks like is a worldsheet that looks a little like a string bit worldsheet, and that begins to show some of the features of the spin chain description of free superreals. Anyway, with this I stop and thank you for your attention.
Thank you for this very nice talk. Questions?
Thank you very much for the nice talk. I actually have many questions, some of which I will ask maybe in private, but more generally, like the less technical ones that first come to mind are related to your outlook. So in the ADS3 case, I think one thing that was really remarkable was how powerful this whole idea was for looking at correlation function even in the non-planar sector, and while staying on the free point, essentially. So I guess the first question is what you think can be done in this direction, whether you can give some ideas of how far you think you will be able to push it. And another thing, maybe I'll just ask too, is the opposite direction, which is if you wanted to include instead some interactions in terms of 't Hooft coupling. So in principle, you have this algebra, and if you look at the Spinchain realization, for instance, you sort of know where you should modify your algebra in order to try to capture the correct type of interactions, at least up to wrapping and this sort of subtleties. So if you can comment also about these, perhaps.
So here we are at the free point, but then the planar limit corresponds to looking at sphere diagrams from the point of view of string theory. And the non-planar contribution come from the torus, the genus 2 surface, and so on. So the question is whether we can include non-planar corrections, is whether we can understand this worldsheet theory also on higher genus. Now, it being a free field theory, that is not totally hopeless. In fact, for the case of ADS3, this localization property for the case of ADS3, we first analyzed on the sphere, but then subsequently Lawrence Eberhard did it for higher genus surfaces, and my student Bob Knighton did it in the free field description for higher genus surfaces. So this is something that, I mean, higher genus CFT is something people normally just say go away, but because this is such a free field theory, such a free theory, there is actually a chance to prove this. And in particular, this localization property is something that seems to also work at higher genus. So I think the higher genus corrections is something that is, I mean, obviously I can stand here and say whatever I want, and I say this is doable, but I think this has a chance to be doable because for ADS3, it has been done. I mean, there is a way of getting the higher genus worldsheets under control. And given the similarity of the structure, you would believe that this will also work for ADS5. So I think the non-planar corrections at the free point, certainly, I think are very much within grasp. I mean, there's work to be done. I mean, that's what we are trying to do, to understand exactly the structure of these correlation functions, to understand exactly what is the appropriate localization property here. I mean, so in the ADS3 case, it's holomorphic maps from a 2D CFT, from a 2D worldsheet, a Riemann surface to another Riemann surface. Now it's a Riemann surface into some twistor space. What is the correct description of holomorphic maps and so on? So that's what we are currently trying to work out. But I would be very confident that that will also work at higher genus. So this is the 1/n corrections. Now, as regards the 't Hooft parameter, well, you see the 't Hooft coupling, I mean, the coupling constant in n equals to 4 is a specific field, and it will correspond to a specific operator on our worldsheet. So it's not something we are free to choose. There's a specific operator on our worldsheet that will correspond to switching on this coupling constant. So what you can do on the worldsheet is do perturbation theory on the worldsheet, where you take your free theory correlators and you insert the operator that corresponds to switching on the 't Hooft parameter, and then you should see order by order the perturbation analysis being reproduced on the string theory. And what you would believe, again, probably because they will delta function localize, and because it very much looks like a spin chain, what I would believe is that if you do this calculation, you will just recover the spin chain way of calculating anomalous dimensions. That's what you would expect to happen. And what you would expect to happen is that this will, in some sense, manifestly reproduce the spin chain description. If you correctly understand how you do this calculation, it will not just example by example produce it, but as for the case of ADS3, it just structurally gives you the sort of objects with which you calculate correlators in the 2D CFT. And here my expectation would be is that it gives you whatever the spin chain calculation for the anomalous dimensions will give. So that's, again, I think also a doable calculation, although for the case of ADS3, that hasn't quite yet been done, but that's something we are currently working on to understand how this works for ADS3, where we are more confident exactly of how this works. But I would also be, I mean, obviously in a research proposal, you can write whatever you want, but I think this is also something where I would be confident that this is honestly possible to do within a reasonable period of time.
Questions? So I have a question. So you always say correlation function, but why not spectrum? We already know the spectrum.
But the spectrum we've reproduced, right?
No, I mean, if you turn on the 't Hooft coupling,
right.
We already know the spectrum, even exactly. So,
sure.
So I'm wondering how, whether you could reverse engineer somehow the perturbing operator in this language.
Well, as I was trying to say, we don't want to reverse engineer it because in some sense, we are already told what we have to do. The question is whether it will work out or not. Because the perturbing operator is the operator that switches on the coupling constant in the dual CFT in Supang-Mills, and that corresponds to a specific worldsheet operator in our 2D CFT. So what we have to do is we have to calculate the correlators, the perturbed two-point functions with the perturbation corresponding to the field that switches on the TÜV parameter. And from two-point functions, you can read off all the eigenvalues, you diagonalize the eigenspectrum, and in that way, you should read off the anomalous dimensions of Supang-Mills. And what I'm trying to say is, we could obviously try to do this case by case, but what my hope would be is that you manifestly reproduce the calculation that you would have to do from the Spinchain perspective. So in some sense, you just manifestly reproduce it correctly because it just reduces to the Spinchain calculation. So you would manifestly want to reduce your worldsheet calculation to what you would get from the Spinchain, and then the Spinchain does the right thing, and therefore your worldsheet calculation does the right thing, and it doesn't just do the right thing for one or two states, it does it for everything in one go.
But do you expect it's a local operator?
Yes, yes, absolutely.
So, but there are not many operators. You could just make an ansatz and then fix them, right?
Well, I think in principle, we know which operator it is. It's not something that's important. We haven't yet had the time to sit down and try. I mean, it's a not entirely trivial calculation we first have to understand how these correlators work, because there'll be delta function laws. So as I said, one has to understand what the correct analog of the holomorphic maps is. But once one has understood this, then this is a doable calculation, and it will either lead to success or it will fail. Right? It will lead to a specific anomalous dimension. It will lead to either the Spinchain description or it will not. Now, okay, my expectation is that it will lead to the Spinchain description, because everything wants to me, this is like a happy compromise of things that naturally come from ADS3 and connecting to all sorts of things that are sort of flying around for the Spinchain of n equals to 4 Supang-Mills. So it would seem to me a pretty harsh fate if this somehow didn't land on the Spinchain. It seems hard to me to believe that it won't, but we haven't yet done it. This is something that remains to be done.